Okay, welcome to our third demonstration. And July 21st, we did the last one June, ancient, long time ago. I mean, when, I barely remember. So I think it was June 25th. So as you can fathom, we're trying to move this very, very quickly. And it took a lot of years to work through all the theory and technology, experimentation, analytical, figuring out how to identify this new state of matter, and then get the kinetics up high enough so we can make something commercializable out of it. Now we're on that track. We're going to try and make a lightning bolt right into productization. So along that vein, we're going to show you what the third generation of the engineering has wrought, and after a lot of sleepless nights and very, very tight deadlines. We do have a demo ready. It was running as of Friday, and we'll be showing that later in the meeting. Just to kind of give you the background for newcomers, first of all, we're making a new state of hydrogen. It's a new energy source. If you want to think of the hydrogen atom as some superstructure, they give you relative dimensions. The electron would be at the top of, say, the 100-story building, like higher than the Empire State Building. And the proton, which is the oppositely charged, positive, versus the electron being negative, is at the street level, about the size of a dime. And out of 100 floors, we're moving the electron closer to the proton, that's closer to the street level. It's, as you would know, gravity is a potential energy field, so is electrostatics. And you get energy off. As you know, if you jumped off that building, you would have kinetic energy by the time you hit the ground. Same with the electron. If it drops to a lower level, it gives off energy. So then the question is, why doesn't it do that spontaneously? Because it could release a lot of energy. In particular, we're talking about going from the top floor, like the 100th floor, down to the 25th floor, reducing to about 1/4 of its natural radius, which will release about 16 times the energy of the binding or creation of a hydrogen atom from its constituent particles, electron and proton, which is an enormous amount of energy. It's about 200 times the energy burning hydrogen. It doesn't do that because the electron is moving in space and time and has a structure that it can't radiate. Current theory doesn't deal with that at all. It just postulates or says it has a defined mathematical ground state, which really means nothing physically. It's just a convenience to try to curve fit data from the late 1800s, namely the Rydberg formula. So we actually have the solution of what an electron is, the structure of the electron, and it predicts that hydrogen can have more stable energy levels if you put it in proximity with something that can accept the energy in something called a radiationless manner. So what's that mean? Well, radiationless would be like if two cars smashed. That would transfer energy, and that would be radiationless. There's through space energy transfer if you push one magnet with another magnet. It doesn't involve light, but you can accelerate it and give it energy by a dipole field interaction. So we're talking about through space field interactions that transfer energy from the hydrogen atom to an acceptor we call a catalyst. Catalyst has a unique standing in the chemical literature and definitions in terms of not being consumed. That is, it changes things, that is, facilitates reactions, but is not ultimately consumed. That's what we're talking about here. Something can accept energy, and it's a lot of energy, so I'll talk about the particular aspects of that are quite extraordinary, but it's the same kind of concept where you have energy transfer acceptor, and the hydrogen atom goes to a lower energy level. So overall, the important thing is we're taking hydrogen, releasing 200 times the energy burning hydrogen. So therefore, you can use H2O, just regular water, as the fuel. And I'll talk more about what the catalyst is and what the particular reaction is and what the impediment was to get the kinetics up to the extraordinary high rate we're experiencing now. So having achieved that, we're looking at different systems for harnessing this energy. And we showed one originally on January 28th. We showed the very energetic reaction. We were looking at doing power conversion by taking a type of concept that's very much similar to what you use in central power gen. It was a motion, what they call, if you want to put it in a category, it'd be a motionless generator. Motionless in the sense that none of the other parts move other than the reaction products. So you ignite this plasma. Our ignite fuel creates a very, very energetic expanding plasma. We looked at the energy in that plasma. It turns out to our benefit and the world's gift, if you want to think of that from nature, it has extraordinary low amount of energy in terms of pressure and volume. So the amount of pressure we develop is very, very low. Therefore, the amount of pressure into a volume as it expands, the corresponding energy is low. And that's a very, very good thing. We subsequently did spectroscopy on it. We found that we observed enormous amounts of black body radiation. This is something that has all wavelengths over a very large spectral range. And the particular range that this has its emission is in the visible spectrum. It's white light. It's blue to white light. It looks like sunlight because it has the same temperature, a very similar temperature to sunlight. That's a very good thing because solar cells have been developed over 50 years and cost, if you add up everything, it's on the order of $1 trillion to harness that energy from the sun in the form of light to electricity conversion. It's incredibly fortuitous that we can apply that to our technology. So we originally looked at a type of a generator technology, exploiting the expanding plasma that's electrically conducting, putting it through magnetic fields, converting that electricity. Later developed spectral data and pressure data showing it's essentially all in the form of optical or photons, light, and then harnessing that with photovoltaic cells, and we showed that during our last demonstrations. The new developments are that exploits a feature of the fuel. The fuel is a metallic material, metallic in that it's extraordinarily conductive. It's a very fine powder, and it has a chemical in it, a compound that can bind water. Water is the source of the hydrogen fuel. So we have water bound in there as in essence, the source of energy that you're going to see. So we have to replenish that. Same as you have to fill your gas tank of your car, you have to replenish the water. Fortuitously, the material that delivers the water is not consumed. So you can use it over and over again. So these compounds and metallic conductive matrix are recycled by exposing it to water vapor. So we had a system that basically, if you go on our webpage and I'll show an animation, we have the system broken down in terms of ignition system, a photovoltaic conversion system, that is photons to electric conversion, and we have a regeneration system. Regeneration system is basically rehydrating the fuel. So what we're going to talk about is two new developments. And the most important developments on the road to commercialization are the ability to continuously ignite the fuel and feed the fuel into the plasma ignition system. So there's a mechanical system we've developed to achieve that at very, very high rates. So we could develop very, very high power. So remember, well, I'll explain to you. There's basically a pulse of power, extraordinarily bright light. We're going to show that, and Johnny's going to show that in a few minutes, that is extremely, extremely off the charts power density. It's about 100 billion watts per liter. To put in comparison, an internal combustion engine about 10,000 watts per liter, and in a jet it's maybe 5,000 watts per liter. So it's like 1,000,000 times higher at least. And that power is being emitted in a very, very short period of time. It's 0.005 of a second. So that's very, very short, and if you capture that on video, we'll look at films where it's been filmed with something called a phantom camera that's used to film high explosives, a very, very high frame rate. 6,500 frames per second is what we filmed it at. We're going to show you that. So it's occurring on a very, very small time scale. But if you look at mechanical systems, they occur on a very, very small time scale as well. For example, we're proposing to ignite this at 2,000 times per second, or 2,000 hertz. That's really not that high a frequency. The internal combustion engine for Formula One racers are rated to have a maximum RPMs of 18,000. So we can easily achieve those types of firing rates and that type of motion of fuel, transport of the fuel, with conventional mechanical systems with very, very low tolerances. So it's not very difficult to achieve that. And I'll go through all the mechanics and the operating parameters of the fuel flow, rates, and the amount of material we're regenerating, and amount of energy we're getting, and amount of power, and the size of the device once we get into showing the third generation demonstration. Then we're going to talk a little bit about the theory and a little bit about the analytical and what its implications are to astrophysical identity of dark matter. Dark matter makes up almost all the mass of the universe, and it's an enigma, and there's billions and billions of dollars of your taxpayer money being spent on that, and it's absolutely been a complete zero, nil result so far, because they're looking for an exotic particle that makes up more than 10%, or makes up more than, if it makes up more than 10% of the universe, then all the current theories, standard model, and what they call lambda, which is cosmological constant, CDM, which is cold dark matter theory, is down the drain. So it turns out that that's a pretty far reach to say that more than 90% of the mass of the universe is something no one's ever seen before. And it is really a reach. But of everything you can see in the universe, it is hydrogen. Essentially everything you see is hydrogen, and there's just a little bit of helium, some other elements. And what the identity of dark matter is, in fact, is this more stable form of hydrogen. It makes sense. If something makes up 100 times more mass of everything you can see, and everything you can see is hydrogen in essence, it makes a lot of intuitive sense that stuff you can't see is a different form of hydrogen. And astrophysicists are saying that as well, that based on collisions of galaxies, based on dynamics of those collisions, and large gravitational bodies formed after those collisions, that it has to be hydrogen in some unusual state that they can't understand why it doesn't absorb and emit light. That's exactly what we're creating here. We're creating a state of hydrogen that doesn't absorb or emit light. Moreover, in its formation, rather than forming discrete spectral lines, these are very, very sharp, essentially identical single wavelengths for different transitions you can identify in atoms and molecules and the like that are characteristic of and identify those compositions of matter. Unlike that, we're seeing something called continuum radiation. That's all wavelengths, as I was saying. In the visible, we see all wavelengths, and we can convert that into electricity using photovoltaics. If you allow this particular ignition of this fuel expand into a vacuum, you will see that black body, that continuum band, all frequencies over a large region in the soft X-ray region. That is incredible because what it does for two things, it shows a new type of transition that is unique to hydrogen, and it identifies the hydrino reaction or transition to this new state, hydrogen to hydrino. We're going to show that live today, and that's going to be Dr. Liu. So and additional, we get a lot of energy. We can make that energy thermal in nature rather than light by capturing it inside a closed container, and we can measure that in traditional conventional equipment. And we have that equipment here before you on the right-hand side of the audience. And that is what they call a bomb calorimeter, good name, because we basically explode the fuel inside of it, and it's got a very, very strong reaction chamber that contains that shock wave, that pressure, not that much, but it does contain whatever pressure it does develop in there, and converts it into heat, and we can measure it with a standard commercial instrument. So Johnny Latowski behind me, he's going to run that, and he's going to show you the results and get me, once he has it, we'll display it on the screen and show you the thermal energy balance. So typically what we get is somewhere between 500 joules and 1,000 joules. It happens about 0.5 thousandths of a second. So let's say 700 joules for average. So if you take 700 joules divided by 5 thousandths of a second, that gives you 1.4 million watts. That's occurring at about 10 millionths of a liter. So if you take 10 to the minus 5, divide that into your 1.4 million watts, you got 140 billion watts per liter. So it's really, really incredible power, and it's just so fortuitous, it's light. The other thing we're going to look at is another type of demonstration we've shown before, where we set off these pulses at second intervals, and then we're going to convert that into electricity, and you can actually measure how much energy those pulses made by the efficiency of the photovoltaic converter and the light that it's emitting. Knowing the optical power emission of the LED array we're using, you can actually do on the back of an envelope in about 2 seconds how much energy is coming out. You also should be aware of looking at the plasma, and you'll see that, well, don't look directly at it, but you can look at it at the video screen, and you'll see it's white the blue-white. As soon as you see that color, you know it's the color of sunlight, so you know its temperature is up around 5,000 or 6,000 degrees Kelvin in that range, and at least above 3,000 Kelvin. And that's very, very good because, as I was saying, that's visible light. You can convert that into electricity using photovoltaic cells. So it's something very, very unique, because if you set off a high explosive, you're going to get billowing black smoke, red light, reddish orange looking. You can go on Los Alamos' website, look at high-speed video of explosives. You'll see what I'm talking about. It's dramatically different from what I'm showing here. So there is no known energetic material that does what we're showing today. So I guess that's about it. We'll go first, we're going to show this very big blast, and then we're going to do some controls first, show the actual emission of light, and show what controls do, because people have asked. Then we're going to come back, we're going to go through the presentation, we'll do the calorimetry and the like, and the EUV spectroscopy, look at some of the demonstrations. While we're setting up one, loading with fuel, we'll come back and run it under argon. Because one of the questions is this burning? Again, this is a very, very fast event. So imagine you're going to take a flame and you want to burn something. How much can you burn in 0.005 of a second? The answer is not very much. So on the time scale this is occurring, you can run water, for example, with certain metals, and there's hardly any detectable reaction. How do you know that? Because you can look at it with extraordinary fast spectroscopy. If you run in air, you can get some oxygen burning, and you can see what they call metal oxide spectra, but not when you put it in water. You don't see that. So it's so fast. Water's got hydrogen. Hydrogen reduces metals, so that reaction is very, very slow, and that's even known from high explosive research. So that's been known for a long time. So what we're running is things like titanium, copper, silver, and then we're running a compound. That's the metal conducting matrix, very, very high fine powder. And then in addition to that, we're running a compound that binds water, like what they call an alkaline earth. That's like magnesium chloride, or we run zinc chloride in some of these, and other alkaline earth halides that bind water. Typically, it's 6 water molecules per molecule of alkaline earth halide. They call it a hexahydrate. And that picked up the water directly from the atmosphere. And as Johnny will show, quick blast. Don't worry, it's not going to injure you. If it were pressure volume, it would. And to give you an idea, it's about 2 psig. That means 2 pounds per square inch above atmospheric at about 20 centimeters away. That's not that big a deal. It's very significant, but it's not very much energy, considering the energy released in the form of light. So that's a very, very short burst. And then, as I was saying, we would have those bursts at very, very high frequency, have continuous, in essence, continuous emission of light and converting that into electricity continuously at about 2,000 hertz. So the rotational feed rate, we're going to do it by a rotary pumping type of mechanism to feed the fuel into the ignition system. The ignition system we're going to use here is limited at about 33 hertz. It's nowhere up around 2,000 hertz, but we will be showing fuel flow rates, or we can achieve fuel flow rates that can go surpass what's required by at least by a factor of 2. So it's very easy, as I was saying, to get mechanical systems. We built that can go at high enough rates to get millions of watts of light continuously. So we're not going to show that because it would be very, very blinding, but we're going to show the mechanism working, and we're going to show it at a frequency which we can achieve with the system we have now. We're building systems that go much, much higher frequency, and we should have those soon. And we'll run those off the photovoltaic converter system. So that's what we're going to show. So Johnny's going to show just what one blast looks like, and then think about that at 2,000 times per second. So that'll be fused light, very, very bright, and then converted into electricity.
All right. Good morning, everybody. Can you all hear me? All right. Okay, so here we have a commercial spot welder, and we use this to put in a low voltage, high current pulse of electricity, and we can quantify the amount of electricity that's going in. We use some voltage taps that are right on the outside of the sensor, and underneath this platform here is what's called a Rogowski cable, and we can measure the current that goes through the circuit quite accurately, and from that we can multiply those two waveforms together, get power, integrate over time, and get energy. And then in other experiments later we can compare that with the energy out and find the net energy we have. So what I'll show here, first of all, is just a metal foil sample. And you can see just basically what this commercial welder does. So I have some silver foil here, just load it in. And what I'll typically do is count down from 3, and on 0 I'll hit the trigger. This won't be loud. This is just a regular metal foil sample that will probably weld to the electrodes a little bit. So 3, 2, 1. So if you look
up there, it's very
yeah,
high
if you look at
current.
the screen up there, this just acquired the waveform. And I'll zoom in. It recorded about 4 seconds, and the pulse here is only about 30 milliseconds. And the white trace is the current, and the red trace is the measured voltage. And there was just a little bit of deviation from a sine wave here because there was some contact resistance, which caused a little bit of a brief deviation from that sine wave. So I'll remove this. Rich, you can grab the pliers right there. Thanks. And another 2 electrodes. So that little bit of current and electricity that went through it spot welded to the surface of the electrodes, which is what it
Yeah, this is different than an arc welder. Arc welder is very high voltage. You have to maintain a gap. This is very high current, very, very low voltage. And it basically melts things and melts metal surface. Not made to form destruction of material. Again, in an arc welder, you can see it's really ablating the surrounding material, destroying it, melting it, and then causing it to fuse with a bead. In this case, it's supposed to be non-destructive, run the current through, and it basically melts materials together.
Okay, so now I want a water sample and tap 1. So now I'm going to load a sample that has just water in it, and I'm going to turn the current down a little bit so you can see what it does. And these samples we're loading for convenience in a commercial Cetaram calorimeter pan. It's an aluminum pan. It's meant to hold 30 microliters. I'll just pass one of these around. This is an empty. Tweezers. Tap 1. Well, unfortunately, my finger just slipped and I closed my application here. I got to relaunch it. Okay. All right, so this is about 30 microliters of water. So we'll do 3, 2, 1. And you'll see nothing happen. We'll take a look at the peak current. So we had about 8,300 amps or 8.3 kiloamps that went through that. Now what we'll do is we'll turn the current up a little bit higher and we'll add a metal conductor, and this will be the sample that's loud that initiates. All right, I'm going to turn the ventilation on just because there's some particleized metal that comes out. And so this one's loud, so go ahead everybody, put your earplugs in. Make sure I get some. Okay, 3, 2, 1.
You can see it's good there's not a lot of pressure volume in that. Yeah, he'll fire off another one. So basically this is very high current. I'll explain the mechanism, but when you run, you got to be above 4.5 volts because that's the energy to break the hydrogen-oxygen bond in the water. And that will trigger the reaction. You have the atomic hydrogen. I'll explain how the catalyst works and why we get so huge kinetics with this very, very low voltage, extremely high current. That's basically the key to getting extremely high reaction rate and high power.
Yeah. You can see in the waveform here, the current reached is roughly 24 kiloamps, and at that point the explosion took place and you see a very large voltage spike, and that's because the electrodes are being forced apart, and that causes a reactive spike in the transformer when that occurs. So I'll go ahead and load another one up.
Yeah, so basically what happens is the power is being reflected back, the sample's expanding at supersonic or greater speed, and emitting light, a lot of light at that point. What we'll have in the commercial design is that reflected power go back into capacitors, so we can use that over and over again. Take very, very low power, low energy to ignite the powdered versions of these fuels. It's on the order of 5 joules, and we're getting about 700 joules of energy out. So the energy gain is very, very high. So as Johnny said, it's a very small amount of energy ignited. It expands out extraordinarily rapidly. Light develops as it's accelerating away from the ignition origin, and that reflected power is going back into the transformer. At times that'll trip the breaker, but we'd have a capacitor to restore that and refire it again. So that power is not, that power is recoverable, and that energy can be stored and used again in a commercial type of ignition system we're designing.
Okay, so we'll do a second one here. Three, 2, 1. Now That's a little bit different than we showed last time because we have an argon box enclosure here. Later on we'll close this, we'll purge it with a fast flow of argon for about 5 minutes and then initiate the sample. So typically we have a blast pressure sensor back here and also a microphone that we turn on. I didn't turn it on this time because the box is there, it interferes with that measurement, but typically, as Randy mentioned, it's about 2 psig and about 160 decibels, about 4 feet off for the mic and about 13 inches off for the blast sensor.
Okay, we'll go, you up the EUV Spectroscopy. Okay, thank you very much. That was good. Okay, this is Dr. Ying Liu. He's going to show the extreme ultraviolet spectroscopy, kind of explain what he's doing there. He's already preloaded the sample. He's going to fire it and then show us the spectrum here live.
Hi everyone. This treatment is designed to measure the extreme ultraviolet light emitted by plasma. As we know, no chemical reaction can generate EUV light, and the electrical power source does not provide enough energy to generate UV light. I'm going to find the sample was ignited in the vacuum chamber and analyzed by the EUV spectrometer and detected by the UV detector. Three, two, one. Okay, this is the spectrum of the UV light. You can see some very short wavelength photons down to the 17 nanometer, and this represents 70 EV photons. We measure the extreme ultraviolet light emitted by the hydrogen reactant plasma that proves the hydrogen are formed in the plasma. None of the plasmas from controls, such as those from non-hydrogen reaction chemicals, produce UV light. So this is the proof of the hydrogen formation in the plasma.
All right, thanks a lot, Ying. So everybody got that? Hydrogen has energy levels. Okay, thank you, Ying. You want to switch to the screen? I'll start my presentation. Johnny's going to do calorimetry. And then we'll come back after I do some of my presentation. Johnny will show us the results. Then we'll go through the presentations more, launch into the demos. So fundamentally, the object of that experiment was that hydrogen has certain atomic energy levels that are very well known. The shortest wavelength is 91.2 nanometers. And he's showing light, and we get light all the way down to 10 nanometers. He has an aluminum filter in there to block all visible light. Actually has 2 of them. And so that filter cuts it off at around 16 nanometers. So that light down to what we're seeing where the cutoff is, that's where the theoretical cutoff is. If we take the spectrum all the way down to where the short wavelength cutoff is and use, say, a CEM that's not responsive to visible light, we can see where that cutoff is. And it's extraordinarily much higher energy. It's 122.4 electron volts versus 13.6. Typical chemical reactions are 100 electron volts. So when an electron binds to a proton, makes a hydrogen atom, it's about 14 times that. And this is 16 times that. So it's about 200 times the energy of conventional reactions. So this spectrum alone shows that unequivocally hydrogen can have lower energy states. So the whole thing about defining mathematically a ground state is completely erroneous. The incentive for that was that no line was observed below 13.6 electron volts as early as 1886. But now we're showing that there's a different type of transition, continuum soft X-ray light, particularly for hydrogen, down to these extremely short wavelengths and high energy levels, which shows that hydrogen has new energy states that weren't contemplated by prior old outdated theories. So I'm going to launch into the presentation. So basically we're here to talk about energy. Somebody sent me some new figures where I have the report. The International Energy Agency has a new projections now in terms of the requirement for infrastructure build out till 2035, and it's $48 trillion. So the energy is extremely expensive, makes up an enormous proportion or segment of our economy, and these numbers don't even do it justice. And the one thing you can notice about this is the amount of renewables, solar and wind, is not going to really make a dent. We're basically looking at oil and fossil as a major source of power for the foreseeable future until now. And we do have some contracts that we did with a prior generation solid fuels where we're trying to make the reactants of atomic hydrogen and the catalyst that makes this hydrino state using a type of solid fuel chemistry. And as you can see, we've advanced it now to what we call the sun cell, which is light emitting and converting light into electricity, not by using old boiling water type technology that's been around since the Industrial Revolution, even back to when steam engines were used to pump out coal mines and railroads where they used to put coal and have steam boilers on locomotives. I mean, that technology is very, very old. In fact, using steam for a motive, for using something as a pusher, primary mover, even goes back to Egyptian days. So we're talking about using an incredibly sophisticated, advanced technology, photovoltaic, that is just absolutely perfect for our power source. And but we do have some contracts looking back into the prior technology that would use retrofit of the old conventional boiler central gen model. We'll talk about this. This new type of technology, the sun cell, opens up a whole new realm of what the reality of power will be in the very, very near future. It's not going to look like it looks now. So it's going to be very, very cheap. That's what this slide shows. It's going to be a very, very small fraction. I'll actually go over real numbers of what the cell's made out of, constructed from, and what vendors are selling those parts for currently at the end. So fundamentally, I was taught that you could not solve atomic problems using conventional classical laws like Newton's laws and classical electrodynamics, and that is absolutely not true. It turns out that the electron now is treated as a point particle, not even having volume. It has no volume at all, which means it can't exist intuitively and practically, and it's everywhere at once, which is totally impractical, and it's a probability model, but it's a probability on a single particle, meaning it has multiple positions and energies simultaneously, which violates causality, conservation of angular momentum, energy, and every physical principle. It would be unstable to radiation, and it's unfathomable how you'd understand it mechanistically. In contrast, it's well known that atoms emit light, and that light is very well solvable using classical electrodynamics, particularly if you have something that isn't a point but behaves as a point. It is a solution, that is, the light is a solution of the inhomogeneous Helmholtz equation with a delta function source, and you solve that as an outgoing spherical expansion of a green function wave, and you match that to the electron. So the point is, you can take a physical representation of light that matches it perfectly. It isn't that the light is math or the electron is math, as it is in the current theory. It's really something physical. It's electric and magnetic fields. In the case of photon, it's charge, it's current, it's mass moving in time and space. In the case of the electron, and because the electron can absorb and emit light, you can treat it as a source current of that light and match the light equation to, that is the equation that describes it, not that it is the equation, it describes what light is, to the source of that light and solve a math that actually describes what the electron is. So rather than treat the universe as if the universe is math, it's described by math. So there are physical laws that you can use to solve exactly what the structure is that is completely absent in the current treatment of atomic problems. And when you do that, you can solve everything. By everything, I mean from the building blocks of matter, subatomic particles, to predicting the acceleration and expansion in exact analytical expression, 1 followed by 85 zeros. And it's extraordinarily accurate. It involves no adjustable parameters. So this is what a representation, and so I just want to show that exists. You can actually make a computer print out a visualization of what the current is, the electron in space and time, and what it is in terms of all its properties based on physical laws. And beyond atoms, solving multi-electron atoms, you can actually take the multi-electron atoms then and solve the structure of bonds between atoms. You can solve the carbon-carbon bond, the carbon-oxygen bond, the carbonyl bond, on and on and on for every form of organic bonding, and they add up. Like if you take ethane or octadecane, no matter how many carbons you add, and you add up how many CH2 groups and CH3 groups and how many CC bonds, you add them together, all of them match to a part per 100,000. That's a limit you can measure it. Same with alcohols and ethers and carboxylic acids and on and on and on. And these solutions give the charge in every bond, they give the dipole that you can measure, and it's the solution of every single atom and every single electron in those bonds, and that's what it really is. It's not a probability, it's actually those charge membranes. They're surfaces of charge. And you can add different groups together, and you can compare it. For example, I got my pointer. We tried a laser. This is actually a, you know what this is? It's a Civil War cavalry sword. I don't know how many people killed, but I guess it's got another purpose now that we're in the modern 21st century. So the thing of it is, here's the calculated and here's experimental. There's a 5 part per 100,000 agreement, and this is using what they call the modern 3G, 321G and 631G basis sets. What that means is you take these huge semi-empirical defined mathematical systems in a computer algorithm, and it basically tries to extrapolate from prior curve-fitting type algorithms to try and make something predictable. And you can see every once in a while there's something that's on the curve between the calculated and experimental, but then there's a lot that's not. So that's the reality of it. The reality, the way these things work, is they're really just curve-fitting algorithms. They don't give you the structure. They don't give you where the electrons are. They don't tell you what the velocity of every electron is. They don't tell you what the charge distribution of every electron is, what its magnetic energy is, its energy of attraction between the positive and negative bindings, the electrons in the binding positive centers. None of the parameters. It's just a number that comes out, more or less, without any physical explanation or intuitive value to it. And then what happens is, you end up with circumstances like this. According to current theory, you cannot image molecules. This is what they call scanning atomic force microscopy image of pentacene. So you can actually visualize molecules now. So the existing theory says you can't visualize a molecule because the electron's everywhere at once simultaneously and it goes off to infinity. But that's actually the image of pentacene. And you can see here the hydrogen atoms, the carbon bonds, and this is the computer rendering of the analytical solution. Here's the hydrogen atoms, and it matches to a part per 100,000, all bond lengths, bond distances, and the energy of that molecule, and its overlay to as high a resolution as they can achieve now. And they keep pushing the envelope. But we've overlaid many of these structures, and the analytical solutions match the images as perfect as they can measure them. Current theory cannot do that. So there's your proof. Proof is in an image. You say a picture says a lot, and that says that you cannot solve molecules in quantum because quantum says you can't image them, and you can image them, and the classical solution is an identical match. Nor can you predict this. This is the catalytic reaction. So we have the blue guy here is the hydrogen atom, and the yellow guy is the catalyst. So fundamentally, as I was saying, you have an energy transfer from the electron to the hydrogen atom. It's a through space, non-radiative energy transfer. So you say, what's that mean? Well, the way the fluorescent lighting here works is an example of that. You have 254 mercury discharged light. It's being absorbed by antimony 3+ ions. Radiationlessly, resonantly, that means there's an energy match between donor and acceptor, to manganese 2+, which is emitting white light, so we can see it because we can't, bugs can, but we can't see in the ultraviolet. So so there's this energy transfer to an acceptor that allows the hydrogen atom to drop to a lower state. That energy can't be just a random energy. It has to be the energy of the potential energy between the negative electron and the positive proton in the absence of catalysis. So in an ordinary hydrogen atom, there's a 27.2 electron volt potential energy between the negative electron and positive proton. If you transfer that amount or an integer thereof to the acceptor, the hydrogen atom will drop to a lower state, and the radius of that state will be a reciprocal integer of the number of units of that 27.2 you transferred, and the energy of that atom, the binding energy, will be an integer squared that of atomic hydrogen, which is 1 plus the number of units of energy that you transferred. So in this case, we're transferring 3 units of 27.2 to an HOH molecule, not hydrogen bonded water, not bulk water. In bulk water, I've actually solved that. It has 3.6 hydrogen bonds on average per water molecule, even at the state where it's boiling at 100 degrees centigrade. It's like a tetrahedral diamond type structure, and the protons, that is the H atoms, which comprise proton and electrons, are almost like protons shared between 2 oxygen atoms, or at the limit between jumping from one water molecule to another in bulk condensed matter water. What we're talking about is a free HOH molecule. That is something not bound to anything. We create that state in this high current, very, very energetic plasma. Turns out if you look up the ionization energies of hydrogen and you look up the ionization energy of water, or excuse me, of oxygen to form water, they're the same. They're 13.6 electron volts. And it just so happens if you take 3 things that have an ionization energy of 13.6 and put them together, you end up with a potential energy between the molecular orbitals and the binding centers, that is the oxygen ions and the protons, of 3 times 27.2, or 2 times that 13.6, because potential energy is always twice the binding energy. So even if you're going to look it up empirically, you could come up with a rational scheme that the HOH molecule, not hydrogen bonded, in isolation could accept 3 integers at 27.2 in terms of its molecular orbitals ionizing, and accept that amount of energy from hydrogen, and it would drop down to 1/4 the radius of ordinary hydrogen. So there's an energy transfer of 81.6, and then the electron is accelerated radially until it reaches a radius of 1/4 that of hydrogen atom. While that second step, where the electron's being pulled in closer to the proton, there's continuum radiation that's emitted. And that's what Ying was showing. So there's another example. You can see these broad band of continuum radiation. So you have these discrete sharp lines. That's what you'd conventionally get. But we have all wavelengths. So this is what you call a black body. The way you can create black body is you can create it by incredibly high temperatures, like millions of degrees, or you can have this very, very new process where the electron's dropping down to these new states, emitting that continuum radiation as black body radiation, all frequencies. So well, it looks like black body. So here's the reason why I say that the spectrum looks the same as black body. So here you can look in space because it presents itself with an enigma in terms of the sun and in terms of interstellar media, and it's tied in to the identity of dark matter. And the mystery is this. If you look out in space, and there's a lot of articles, if you look through the literature right now, there's a lot of articles where different spectrometers are coming back and they're saying, you know, there's extraordinary amount of light that's high energy that's ionizing everything. So they finally got to that point. It took about a decade. And prior to recent explanations I've read, prior to that, the extraordinarily high ionization you see of the gases in between galaxies in space and in between solar systems, like the interstellar media, in between stars, that was explained due to thermal ionization, that it had to be extremely hot because there's no explanation why it was ionized. Now it's finally dawned on everyone, well, maybe there's some other source of radiation that's ionizing it, because if it's extremely hot, it would have to be millions of degrees extremely hot, and it would have to show visible light, and there is no visible light. Space is dark. So now it's the conventional explanation is that it's some extraordinary high energy light that's ubiquitous throughout the cosmos of unknown origin, and it's ionizing the interstellar media. That's what we produce. We produce extraordinary high continuum, highly ionizing light. Same thing's true of the solar corona. Solar corona looks like it's 2 million degrees because it's got extraordinarily highly ionized atoms in it. But then there's carbon monoxide molecules and hydrogen atomic transitions like that would say it's nowhere near the millions of degrees, but have to be to explain that high temperature and that high, they would give that ionization. The alternative explanation is this hydrogen reaction is creating continuum radiation in the sun, and that's ionizing the corona to look that temperature. And we see exactly the same thing in our lab. That is the explanation, and the material they call dark matter is this new state of hydrogen. In fact, if you look, this is actually what dark matter looks like. You see that ring? That is a ring of dark matter. There's basically nothing there. You see some galaxies, and they're really far stretched out, like that one. And if you move the telescope at different angles, it'll disappear because it's not really there. It's being gravitationally lensed from somewhere else. So this is Hubble Space. This is the Hubble Space Telescope by the European Space Agency study. And the glowing material around it and the material that's emitting from those galaxies is essentially 100% hydrogen. But there's enormous amount of gravity that's causing that gravitational field to cause light to be bent such that those galaxies appear there when they're not really there. That's what dark matter is. That makes up almost all the mass of the universe. And what we're creating in our lab is we're creating a new power source by causing hydrogen to go down to this new state that doesn't emit or absorb light. And that's dark matter. So we can identify it not by visible transitions, not by electronic transitions, where it absorbs light or emits light, but we can make it rotate, and we can make it vibrate, and we can look at something called NMR shifts, where you put the material into the composition matter that contains hydrinos into a magnetic field. The proton has a magnetic moment, and it can process in that magnetic field at a certain frequency depending on what the local electron effect is. In our case, the electrons are much closer, so the shift is different, and we see that. You can see the rotation and vibration at 16 times, or 4 squared. Remember I said it went down to the 1,4 state. You can see the ionization energy at 16 squared, that of ordinary molecular hydrogen. So there's about 11 tests in all that we do to identify this new state of matter. One of them is called Raman spectroscopy. This is for the benefit of any of the spectroscopists out there. But basically, this is the Raman spectrum of the starting material. And you see this dip here at 1950 reciprocal centimeters. That is the rotational energy of H214. So the ordinary hydrogen has a rotational energy of 121.7 reciprocal centimeters. 16 times that is 1950, and we do in fact see the rotational energy of the hydrino exactly where it's predicted to be. After we run the reaction, expose those materials to this gas. Here's another example. So we put in a metal foil. We run this reaction, as you just seen. The metal foil has no dip there, and then after it's exposed to that gas, you get that dip, and that's the rotational energy absorption of this hydrino molecule. Another example. Then we capture the material, trap it in a crystalline lattice. Here's predicted experimental. You can see on the right-hand side, very, very small residual. So these spectral lines are the rotation and vibration of, these are rotational levels, particularly within one vibrational level of the H214 molecule. So you see these are integer spacing, has the same exact spacing. That's absolutely, there's nothing else like that. That's rotational energy levels. And these rotational energy levels are 16 times higher than those of hydrogen. Hydrogen has the highest rotational energy of anything known. So this is an Aramis spectrometer from Yobin, Yobin, which is extremely, extremely expensive, and there's only a few of them around, but we've done it on multiple instruments. It's absolutely reproducible, absolutely perfectly the PQ and R branch, which are allowed because this is essentially like an excited state, but it's stable by the nature of the photon, binding the electrons tighter rather than the photon making the electrons less tightly bound in the case of an excited state. So it matches theoretical predictions absolutely perfectly, and it's characteristic of identifies hydrino. We can also knock both electrons off the H214 molecule, and that's predicted to have an energy of 500 electron volts. You have to knock both of them off, because remember, electronic excited states are not allowed for this molecule. So an ionized state is the same as an infinitely excited state, so we knock both electrons off. The predicted peak is 500 EVs. This is run at Lehigh on their Sienta 300 and at Duke. Both of them say the same thing. And it's their programs cannot identify it to anything known, and it only shows up after we run our reaction, this explosion, and expose it to the gas from that ignition event. This is another example. So in more detail, this is what Ying was showing you. It's an extreme ultraviolet spectrometer. You have to expand the gas into a vacuum because soft X-ray cannot go through a millimeter of air. So this is extraordinary, extraordinarily safe. And when it is run at high pressure, that soft X-ray is converted into visible continuum, or in other words, visible black body radiation. So that spectrum basically shows light. Here's where, if you put a quartz filter, so it can't go through quartz, is the same exact reaction with a quartz filter in. There's no EUV light. Quartz specifically attenuates EUV, does not attenuate visible, so you can show it's not visible light. And then you get these spectral lines from ionizing the material there. This is continuum all the way, this is zero order. So we're getting light all the way down to about 15 nanometers. If we move the filter, we can get it down with a cutoff of 10.1. That's the theoretical cutoff of 122.4. That's the energy you get for hydrino forming, particularly the state 1/4, H to 1/4 transition has that cutoff, 10.1 nanometers, which is 122.4 electron volts, which is about, for this particular transition, in comparison, typical chemical reactions are about 1 electron volt. So it's a huge, huge amount of energy, and it's showing spectral emission much higher energy than was thought possible based on conventional theory, and proves that hydrogen can have more stable states. So let's look at this blast Johnny was showing you at 6,500 frames per second. So you can see most of the light is occurring, essentially all the light is occurring away from the electrodes. That's very, very important. If they were occurring in between the electrodes, based on engineering calculation, we'd only get about 8% of the light. So basically this explodes. It's moving initially at above sound speed. It's moving about 1,300 meters per second. It slows to sound speed 343 meters per second. And as Johnny was saying, the pressure is about 2 psig, which will give you about 1 joule if you're expanding it into a liter volume. 1 joule compared to 700 joules of light. So that's basically the energy balance. Okay, now I want to show you 2 aspects of this. The first guy was caught off guard because we were testing this new type of fuel. And watch the top up here. So I'm going to play it back again. But if you look up top here, here's where the little tiny pellet is, and it's going to roll in this closed roll in this position. You're going to see light coming all the way up above. You got to look at the color and see where the light is. You see that? It's a bump over the blast shield. Now the reason why you saw that, even though it's a half a millisecond event, is because it's so blinding, it blinds the camera on the other side of the room. So it's extremely, extremely bright. It basically saturates the camera, and then you can see the extent. And if you look at it on some of these cameras, the whole room is, you can't see the whole room. It's completely whited out. So it's incredibly, incredibly bright, and almost all the light is coming not from between the electrodes, but in the volume around it. So we're exploiting that in terms of how we're going to capture the light and convert that into electricity. So this is the engineering device, and basically it has on top, and there's some labels here. On top there's output terminals, and you can see these bars. They're the bus bars that carry electricity from this photovoltaic cell, or actually is a panel. And then there's a heat exchanger on the back. All these, what they call concentrator photovoltaics, they can run up to 1,000 times sun intensity, and they come with their heat rejection system. So whatever needed to be, whatever engineering is required to reject the heat in the case of what they call concentrator photovoltaic is identically the same in our case, because the light from our cell is the same as the light from the sun over whatever wavelength band we use in terms of our emission and what cell we choose to match that emission. So if you have, for example, a 1.1 electron volt photon come from the sun and a 1.1 photon EV photon come from that, the photovoltaic cannot tell. And we're going to have a validator in later. We have 3 validators here today, very esteemed professors that have done validation work. And one of them is Dr. Nick Lumack. He's a very prestigious professor at the University of Illinois. And his specialty is energetic materials. He does all kinds of fast spectroscopy on RDX and penterythryl tetranitrate and all kinds of very, very high energy materials. So he brought out some extremely expensive equipment. He has some equipment no one else in the world has, courtesy of the military that study these types of reactions and the evolution of spectroscopy over time, and recorded beautiful, beautiful black body radiation from our sources over the entire range, incredibly high time resolved. And he'll speak of that too. It doesn't matter where the light's coming from. And this is extraordinary, extraordinary high power light that can be converted into photovoltaic systems. So this would be a commercial system with its heat exchanger. And then we have a regeneration system that's shown externally here. It has a water reservoir, which I'll show more in detail here. And this is not, we don't have those systems here other than in function. So what I'm describing is in function. So you at least get an idea of what the machine has. Like internal combustion engine has pistons, crankshaft, has cams, opens valves because you got to have gases come in and out. So it has different functions. What we need is 3 functions. We need to provide a very high current, very low voltage electricity. So up on top there, that gray box, the light gray box, is a source of electrical power. And that flows through these bus bars, through these gears, and the fuel is trapped or interdigitated in these gears. We actually use rollers because the blast blows the teeth off. We found that the rollers actually build up a metal coating, and then there's a way you can spin one electrode relative to the other at different rotational speed, and they'll actually dress each other. So it's like the perfect thing that the rollers won't wear out. They actually build up metal from the molten metal from the blast, and you can actually reprocess the gears in the machine. But here's just showing schematically. Again, you trap the fuel, run the current through it, blast, and then the makes ignition, and then the light will go to the photovoltaic. And we have some heat exchanger. We have a drive system to drive these gears. Then the fuel will come down this chute, and then it'll be transported up in the regeneration chamber where it's rehydrated. Here's the blast. So it gets rehydrated here, and then it goes back up into the fuel bin again for another cycle. So the fuel we're going to run today has been run many cycles. You can regenerate it just by adding water. So what we need is an ignition system that has a mechanical, fuel entrapment, and compression. You've got to compress the fuel in order to get the resistance low enough. You have about several hundred microohms, so it's very, very highly conductive. You run the high current through it, and then you need the source of high current, which is this power supply, the bigger rectangle. And then you need, so that's ignition system, mechanical and electronic. Then you need regeneration, which is a way of rehydrating it. So you need transport, rehydration, and then you need photovoltaic conversion. So 3 systems: ignition, which has mechanical, electronic, and you have regeneration, and you have photovoltaic. Three functionalities. And we can incorporate that into the demo, but we made it really, really simple. So here's kind of the labels of things. Then you have the bus bar coming from the photovoltaic, going back up all the way top to the blue box, which is the power conditioner and power controller and output terminals. And this is a more detailed schematic. Well, this will be on our webpage, so you can get more details later. So this is an SUV application. So you want to turn the lights off? You kind of watch it better. I'll just show you how it works in an animation. Okay, here's the gears, and the fuel's going to come down and get interdigitated in the gears. Then the plasma is formed from running the current. Then it comes down the chute, goes back in the regeneration chamber, gets rehydrated, and back up into the fuel bin. And then the PV converter converts to electricity and puts the electricity back up into the source electrical power at the top, and some of it goes out that output terminals to the power conditioner, power controller. So electric vehicle, you just have the transmission, electric motor, and power controller like in existing electric vehicles. if you look at the, you want to turn the lights on? The advantages of that type of vehicle, actually that was very oversized. I'll even talk about dimensions of how much power you can get out of this, but it's quite extraordinary. So this is looking at the Tesla Roadster. It's a megawatt of energy per mile. And what that translates into in terms of how many moles of hydrogen there are per liter of water and how much 50 megajoules per mole of H2 to H2 1/4, it translates into 3,000 miles per liter. And that's for 200 kW, which is 267 horsepower. And there's no pollution, and it can be extraordinarily cheap. So we'll talk about a model in terms of how we're going to make a 250 kW to 10 megawatt, we call block, that can be used for essentially everything, and how we're going to commercialize that and then license that. This is the first generation or second generation of prototype. We're using an auger feed system. So now we're getting into where we're doing continuous feed. So this had a very trace amount of fuel coming from this auger over top, feeding into these gears that are, as you can see, rolling at very low rotational speed. So here's another variant of that, higher frequency. You can see there's metal buildup here, and it seems like that actually protects it, and we'll have a way of dressing that off, so we always maintain the integrity of those rollers. But the concept is, you can see there's an auger up above, there's a very small reservoir of fuel, and it's dropping down in between those rollers, and the rollers are allowing electricity to pass through to ignite the fuel, and we're getting that really bright light. So the first thing we did is we had fuel pellets, and we ignited fuel pellets in terms of a strip. We fed into a seam welder. I'm going to show you that, and the PV converted it. Second generation was we took auger feed, and we flowed the fuel down. Very trace amount. You couldn't even see it. It's so small amount in terms of being a gravity feed system. And now I'll come back at the end here and show you what our new system is, and we'll demonstrate that. So as I was saying, we make billions of watts per liter of fuel, forming the hydrino, and we can photovoltaically convert that. So photovoltaic is an off-the-shelf technology. It basically takes light, converts it into charge carriers that recombine to an external circuit and give you a voltage and current, which is power. And this is just showing a comparison of light taken from the sun. Here's the water bands where the water is absorbing the sunlight, and then here's a spectrum of ours. And we have different spectra. Some of them have black body, even down to 800 nanometers. We have some that have a peak here, and we have different materials and different conditions that can move our spectrum around. The problem is with the sun, you pretty much have to accept it. So you try to build a photovoltaic, they'll match the sun, and in our case, we can take the ideal solid-state physics of a photovoltaic and actually match our light source to it. So we can potentially get much higher conversion efficiency, as I'll address next. So this is an electricity demo. So the idea is we had the plasma, the bright light. Now we're going to turn the lights to Bill. Okay, so one thing to notice about this is we spaced out the fuel pellets such that if they take the rotational feed rate and the fuel spacing, they detonate about once every second. So I was saying that the energy balance from the calorimeter is around 700 joules. So that lighting array is 70 watts. So you have 70 watts for 1 second, that's 70 joules. It's got the PV panels around it, solar panels that are 17% efficient, but we're only getting about 60% of the light transmitted, about 40% is reflecting through the Lexan blast shield, so we're only getting about 10% overall conversion efficiency. So if you take 70 joules divided by 0.1, you got 700 joules. So there's your energy balance. There's 700 joules per pellet, and it's being converted according to the conversion efficiency of those photovoltaic cells. That gives you an energy balance right there. When we're using powder fuels, like you saw in the earlier demonstrations, we were doing the gravity feed, the amount of energy to detonate that's only on the order of 5 joules, and you get hundreds of joules per blast. So the energy balance can be very, very high. In photovoltaic cells, rather than 17%, there's the concentrator variety that don't run at 1 sun capacity, run at 1,000 suns, and they're working in the field at 40% conversion efficiency. So it shows you that there's an existing technology that's very, very appropriate and ideal for our light power source. So next I'm going to talk about engineering. Lights up. Yeah, where were we with the calorimetry? Oh, you got it? You want to show it? Sure. Okay, Johnny's going to show you this is a good place to break. So Johnny's going to show you the calorimetry, and then we'll go into engineering. I'll put my sword here.
Okay, so I had a sample loaded. It was the same type of sample that we had placed over there and initiated. It's loaded in this commercial power calorimeters 1341 bomb calorimeter. And essentially we have a flange that's enclosed, and we pass the current through copper bus bars into the system, but it's all enclosed beyond that. We have a purge vent here where we purge the system. It's a very small volume system, it's about 100 milliliters. We purge that with argon, plenty sufficiently, so it's purged many times over and it's closed under positive pressure. And then essentially I initiated the sample while Randy was talking, so we can see from our previous VI the similar voltage in the red trace, the current in the white trace. And from that we can multiply the waveforms together to get the power and integrate to get the energy. And at the time the sample initiated, 207 joules had entered the sample. And if we go look at the PAR VI, we can see this is the temperature trace that's being recorded by the thermistor. This thermistor, the resolution is 1 millikelvin and repeatability is about 2 millikelvin. And when I initiated the sample, you could see the previous slope of the room temperature going down. It suddenly rose in response to that reaction that took place. And then at the end of the reaction, the end point, the room temperature slope resumed. And we can take these two slopes, and you can take the two slopes, we plug them into the interface on the computer here, and this does the power calculation that's in the published manual. And you can calculate the energy output from the total thermal temperature differential. And taking those slopes into account, this was about a 0.105 degree temperature differential, and that works out to 836 joules out for a net of about 630 joules, which is about a 4x gain on the system.
Now what he's running is that aluminum encapsulated pellet that he passed around. So we have a very, very discrete, defined aliquot of fuel in there. We can control very well. So they're typically on the order around 200 joules to ignite. And then when we discard that and run just the powders, we can ignite it with 5 joules. We have to melt the entire capsule before the current passes through the fuel, and then once it hits the fuel, then it ignites. And that takes about 200 joules to melt that aluminum capsule. So that's why it's higher for that particular time. So you got about 4 times the energy gain, and the energy gains for these powder fuels can be quite high. Okay, thanks, Johnny.
You're welcome.
So we'll go into engineering now, and basically what we're looking at is a rotary it's a rotary ignition regeneration system, and then we have an optical distribution system and photovoltaic converter. So remember I was saying that we get extraordinarily high light. So then the question is, how high is it? Well, there's something called the Stefan-Boltzmann law, which probably doesn't, you don't really care about, but basically it says if you know the temperature, and you can measure the temperature from the visible wavelengths that it emits. So the spectrum I showed you before has a certain characteristic curve, and where that peak curves and what its shape is tells you what its temperature is in terms of a black body, and then you plug that black body into the Stefan-Boltzmann law, and it'll tell you something called the radiance. That is the watts per meter squared. For example, if it's 6,000 degrees Kelvin, that means it must, by the laws of nature, emit 75 million watts per meter squared. The sun is only a kilowatt per meter squared on the Earth's surface. That's 75,000 times more intense. So we're in that high temperature black body radiation realm, which puts it in 10,000 to 75,000 times more intense than the sun on the sun's surface. I mean, excuse me, on the Earth's surface. Sun's surface is much, much higher power. So, but it gets diluted down a lot by the time it gets to the Earth, and by the time it reaches Earth, it's only a kilowatt per square meter. So these solar cells can take 1,000,000 watts per square meter and convert them into electricity at 40% in the field conversion efficiency, meaning that you get about 400,000 watts of electricity per square meter for something as like thin as cardboard, which is incredible, incredible amount of power. So then we have too high a light intensity. So what do you do about that? Well, we have something called an optical distribution system. Basically, we have to let the solar panel industry catch up with us. Solar panel industry is moving away from large solar farms to big parabolic dishes. These big parabolic dishes on the order of, say, 10 meters or 30 feet across, even bigger than that, and they concentrate the light into one little tiny square, maybe a few inches square. And then they convert that into electricity. So they use a solar cell that has an enormously high capacity compared to traditional solar cell, particularly like 1,000 times more. There are cells that are being tested right now that go 10,000 times more. If they're 10,000 times more, then we probably won't need an optical distribution system. But right now, with the state of the art in solar cells, we need it. And it might be worthwhile because it would lessen the amount of heat rejection extremes that we would have to go to and make it cheaper. So it's so small that it really doesn't really matter anyhow that we have to distribute the light. But this is for the first time revealed to the public, the optical distribution system and our new type of fuel ignition and regeneration technology. So basically what this has is the rollers you saw before, but without the auger over top. In replacement of that, we have a trough on the bottom. And what we found is that you could make something called a slurry. You could take something like the metal powder plus the material, the compound that binds water, mix them together in equal amounts. It'll make the hexahydrate, and then you mix that in terms of the number of think of number of entities of the metal powder binder, water binder compound, and extra water. If they're 1-to-1, you can make a slurry, and we can propel that, rotary pump that up into the ignition system at extremely high velocity, and it'll ignite. Then you can just rinse it down. So you have a water reservoir, a pump, ejection pump, water line, and then there's water jets along this window wash line. And we have an arched window that's optically transparent, and it washes that arch. Material comes back down this parabolic mirror, and then there's grooves on the back of this wheel. So this wheel is rotating such that it pumps the water down this way and the fuel up the middle. So it's pumping fuel up the middle, and then the question was, if we're getting an ignition blast, then the fuel might get pushed out. So that was the idea of the gears. If you have it dropping down gravity, the gears would interdigitate, lock the fuel between the teeth, and then the plasma would go out, and the pressure wave couldn't push the fuel back out of into the feed trajectory. Now we're rotating so fast, if you calculate the kinetic energy, it's like a bullet. It's really, really moving fast, the fuel. So the blast can't stop it. And it's moving upward, and the plasma expands upward, so we can go up through the window with the light and into the optical distribution system. So it does two things. It gives it kinetic energy to hurl it up in there like a bullet so the blast doesn't push it down. The pressure is such that all the pressure and momentum is going up, so the plasma expands in a preferential vertical direction, and all the light goes through this top window and then goes into this optical distribution system. So there's a washdown, and then the water's pumped back into the trough. Then there's a sump pump in the back to pull out the extra water, and that goes to the ejection pump, and the ejection pump recirculates the water to wash it down. So it's just that simple. It's just it's circulating water, and it's one rotary pump. Very, very few moving parts. And then we have these motors independently controlled. Jim's going to show that in a second. They're on servo motors that you can control the velocity, torque, and position to extraordinarily high precision. And you can even make one rotate faster than the other, and it'll grind away, or they call mill or dress the other one, so it'll work off the extra metal powder. So then underneath is the source of electrical power and the output terminals, and then we have bus bar coming down through here into the system from the photovoltaic. It'd be inside this channel. So now we'll look at the optical distribution system and photovoltaic conversion system. Oh, let me give you a little more detail on this. One more piece. So one of the things we have is a chute that can direct the water down. There's channels in the back of that parabolic dish, and that roller pump will pump it back into this trough. Then we could add an applicator wheel if the fuel is we want to put it on at a thicker application, which I'll show. That's very important in terms of how much power you can generate. We can put an applicator wheel on there, and then we have an applicator wheel motor. All this can be built so that all the components are outside of the housing of the roller electrodes. So all this stuff is away from the region where there's plasma and fuel and water and the like. So this should have a very, very, very long survivability and durability. So I like this a lot. This is the optical distribution. So remember, starting out 10,000 to 75,000 times higher intensity than the sun. So what we have is a light coming up through here at very, very high intensity, and it's hitting these mirrors and being reflected to the photovoltaic panels here. So these mirrors are semi-transparent mirrors. They might start out 10% reflectance. You know, you ever seen like a detective show where they're looking at the people getting interrogated and then they can't see in because it's semi-transparent. Like you can, or it's one way. They're, you know, you can look even at a window pane depending on whether it's dark out or light out, or it's dark inside the room. You can see it does reflect. So there's transmission and reflection at any interface. And you can control that. So we would have, say, 10%, 20%, 30%, and then by the time we get to the top, 100%. So that'll sequentially cut the light down, and it's in these columns. So each one of these columns would be have light reflected to these PV panels. So rather than have one PV panel line of sight across the top, like we're going to put one on the top here, these panels are vertical, and they have these semi-transparent mirrors that divide up the light. So that's basically it. It's very simple, very cheap, and you'll lose no light. I mean, there'll be essentially no light loss. It's showing a cutaway and showing a PV panel, and then you can see the cutaway of these mirrors that shine the light into the blue part, which is the PV part. And here we have we're looking inside of the PV panel. So the light would come through this one. Some of it get reflected here and shot over to this PV panel on the other side of this angled mirror. And then the light would come up to the next one, and then it would shine on this section of the PV panel. If there's any stray light, we could have PV panel there too, or a mirror, and it would eventually get reflected up there. Mirrors are very, very good. They're better than 99% efficient. Meaning you'll not lose any power in the optical distribution system. It doesn't matter what wavelength it is, and it doesn't matter over the range we're looking, and it doesn't matter whether the plasma is expanding, whether rays are divergent, so it's very, very tolerant of our particular light source. So you don't need any focusing. So here's some of the parameters. Maybe I use this mouse. So this is looking at what would the dimensions be if you're going to engineer a system? You're going to make 10 megawatts electrical with concentrator photovoltaic panels that are 40% into field efficient. And you need 25 megawatts of light. This is the type of fuel we use, either titanium, copper, silver, zinc chloride, or magnesium chloride with a hydrate. Johnny was talking about in the calorimeter, and you can see in this welder, we adjust the pressure. There's a certain amount of pressure in terms of compressing the fuel. So that'd be the pressure that's applied by those rollers. Calculating the energy got per unit mass comes out to 5 megajoules per kilogram. So this is just an input. Whenever there's just an isolated variable like this, these are the inputs. So you can adjust this, and then these other variables are calculated based on these independent variables, and I'll show you what those are. So we've got 5 megajoules per kilogram, and the input is 25 megawatts light to 10 megawatts electrical. So that translates into a fuel mass flow of 5 kilograms per second and a fuel volume flow of 1 liter per second, and it's got a cycle frequency. Now this is based, remember I said the pulse is 0.5 milliseconds. That's measured spectroscopically, so that means we need 2,000 hertz in order to get fused light. So it's constantly emitting at a constant level. We're making this as an independent, we're going to make the roller 10 centimeters or about 4 inches in diameter. So based on that, the 2,000 hertz, we got 1,050 centimeters per second. The roller, so that's a roller speed. The fuel dimensions is an independent variable. This would be 3 millimeters high. The fuel pellet that we've been detonating here is 3 millimeters high. Then we'll get the length, and that turns out to be based on the rotational speed and the ignition frequency, 0.525 centimeter length. So half a centimeter will get detonated with every pulse at 2,000 hertz, and that rotational speed. Then based on the fuel volume flow and the other dimensions, we get a roller width of 3.17 centimeters. That's pretty narrow. That's a little bit over an inch. And then these are other parameters. These are just the ignition parameters we need. 20,000 to 30,000 amps, 4.5 to 8 volts typically run. So that translates, multiply those together, a range of 90 kilowatts to 240 kilowatts. Then you can calculate the average power. Remember, it's 5 joules times 2,000 hertz. The average electrical power in is only 10 kilowatts. That means the duty cycle, the time that power supply is on, is only 6% of the time, and it only is putting in 30 microsecond pulses at 2,000 hertz to give you constant light output of 25 megawatts. The operating temperature is under 100 degrees centigrade because we're running it in the slurry. The slurry is aqueous, so it would boil above that. We're going to keep it chiller, keep it below 100 C. This is the pressure, 2 psig, black body radiation, 3,500 to 5,000 Kelvin. Now, looking at the area, so we have 25 megawatts, and these cells convert 1,000 suns. That's a megawatt per square meter at 40% efficiency. That means we need 62.5 meters squared. So we're just going to define as independent variable. We're going to make the width of the system, the optical distribution system, 1 meter, and we'll make the length of meters. We got a meter by a meter. So then we're going to space the PV panels at about 1 inch. Then we're going to require 50 panels. And then if you calculate the height based on the area need, the 62.5 meters squared, you can calculate the height is 1.25 meters. So basically you got a cube that's a meter by a meter by a meter, giving you 10 million watts of electricity. That's enough to run the largest bullet train, huge super tanker. You put 10 on them, you can go with a 780 or 777 or 787. You can fly. You can do pretty much anything with that kind of power. It's electrical. So then you say, okay, how about if I want to make a megawatt? Then it's 1/10 that size. And if I want to make 100 kilowatt, it's 1% that size, which is really small. So by the time you get into cars, you're looking at something very, very small. And this is only the beginning. I'll show you how huge these numbers can be if rather than a 3.717 centimeter, you use 100 centimeter roller, like a meter wide roller. Just enormous amount of power. So this is looking at the characteristics of the photovoltaic converter technology. Actually, this is probably better. I'll just use this little pointer here. So this is showing, basically you got monocrystalline silicons, this dark blue one. So we're looking at that. You can run that at 250 suns. They actually the industry ran monocrystalline silicon until they went to triple junction. And I'll explain what that is in a second. And then there's gallium arsenide, which is this orange dotted one here. So that takes out this very, very large wavelength region. Then if you use germanium, which I'll show you here in a second. Yeah, here's germanium, this one. Particularly, here's so we could cover this region with silicon and gallium arsenide, and we can cover this region with germanium. And if we have something right around 800, we're absolutely perfect for silicon and gallium arsenide. Because the band gap, there's something called a band gap. That's the material has an energy level that is excited by the incoming light. And light comes in packets of energy called photons. So the energy level in the crystal is 1.1 electron volts. Sunlight doesn't give you a lot of light at that energy. Sunlight has most of its maximum here at 480 nanometers, which is 2.58 electron volts. And 1.1 electron volts is somewhere in around this region. So you can see most of the light is a mismatch with the existing semiconductor technology. That means you can only get 40% theoretically maximum, even if it worked perfectly. Because the energy, the photon's too high. You lose all that energy. So anything above 1.1 eV, you lose it. You don't get that extra energy. You put in 2.58, you're only going to get 1.1 EV electricity out, even if it worked perfectly. So, so if we put in 1.1 EV light, we're going to get out 1.1 EV electricity. So we can make our light source more perfectly matched. But the point of it is this indium gallium phosphide, indium gallium arsenide, and then there's other ones, gallium arsenide phosphide, they have a band gap about 1.9. This has a band gap about 1.5. And then the regular materials like silicon, they have a band gap about 1.1, and they're in around here. Gallium arsenide is 1.3. Germanium's 0.7. So the point of it is there's different materials that have different energy levels, and we can match our light to the energy levels of that material and get much higher efficiency than conventional materials because they're stuck with the sun. And we're stuck with it. We're not stuck. We have adjustable light source in terms of what optical wavelengths we can put out. So here's some of the commercial materials. This is one by Solar Junction. It's 42% efficiency, and it operates here. You can see at 1,000 suns at around well, more than that, over 43% efficiency. And here's one by Azure Aerospace. This is called a dense array. That means there's a whole lot of cells. It's a bigger area. But I wanted to show this because you can see there's inlet and outlet facets on here for coolant. So we buy these things all prepackaged. We got a lot of questions. Well, how are you going to cool it? You're going to get a credible amount of heat. Well, guess what? You get a credible amount of heat from solar photovoltaic too. It's exactly the same. You put in 1,000 watts of sun or you put in 1,000 watts of our source, it's exactly the same. So we have the same heat. In fact, we might get higher efficiency because we can better match the chip characteristics with our light source and therefore not have as much heat. But I wanted to show that they're pretty thin and they have cooling built in. So then there's the other things that aren't triple junctions. These are super, super cheap on a comparison basis, at least 10 times cheaper. This is gallium arsenide, commercial material. You can see these things are typically on the order of 25. They could be as high as 30% efficient. These operate at 1,000 suns. And with our light source, we could probably get up around 40% efficient even with a single junction. So let me make that clear. What I mean by junction, they use 3 different layers. So they want to get some of the sunlight with this layer, some of the sunlight with that layer, and some of that layer. So we would just use 1 layer. And these 3 layers make it more efficient for sunlight, but they make the cost about 10 times higher because they have this to deal with. Now, if we can make all our light in this region, we can just use 1 layer or 1 material, and it'd be incredibly cheaper and incredibly easier in terms of the engineering. And then this is your standard silicon. They're up around 20%. Some people are saying maybe they're like 22%. And they'll operate at 250 suns. So again, if we can match our light better, we might be up around, what the companies are predicting, at least 30%. We may be 40% with our light source on these types of materials. And then the other thing we can do, which is an advantage, is we can have the mirrors on the bottom. Like the bottom rungs of the mirrors can transmit visible, or they can reflect visible light to the photovoltaics and transmit infrared, and then we can have an infrared PV at the top. So we'd have visible PV panels at the bottom, infrared PV panels at the top, so we can separate the light. And these are commercial materials. They're glass. They put them on office buildings to reflect infrared and transmit visible, or you can get them to do vice versa. So you can get selective, what they call dichroic glass mirrors that can selectively concentrate or select for visible versus infrared and thereby direct it to different parts of the photovoltaic panels. So now we're going to look at the 3rd generation of our cell, 3rd generation technology in action. We need lights on. Yeah, wait a minute. Before I do that, why don't I have Jim just explain it? Why don't you turn it on? Jim's here. We'll have him explain it, and we'll show the videos. Yeah, you want to explain just? Well, I'll explain. Yeah, Jim can turn it on. We can do a little demo for you how it works. Then we can look at the videos, and then Johnny's going to do the argon blast, the blast under argon, so you can see it's the same. It's not oxygen, burning, whatever, because nothing. There's going to be no oxygen. It's going to be argon, which is inert gas. And then Jim's going to load up the fuel, and then we're going to run it. Then we can go out and look at another PV system where you can actually ascertain the energy balance based on the firing frequency and the amount of light we're getting from the PV. As I said before, it's be 70 watts of light at 1 second pulses.
So the motors are all fully integrated. The controller is built right into the motor. So what we can do is we just program the speeds that we want into the motor, and then just pipe into a simple switch. And turn it on. The motor will spin at the programmed speed. It'll go up to 200 RPMs, tell you your target speed. And you can just continue. This one will ramp up to 300 RPMs. and so on. And depending on the hertz of your power source, you can optimize the speed of the machine.
Yeah, so the power is controllable by the rotational speed, and then the firing frequency and the amount of fuel you put on. There's a lot of shorter than millisecond, probably even down to the microsecond time controllability of the power output, and the light's essentially instantaneous. So this is extraordinarily controllable. So if you wanted to have somewhere where you have essentially a throttle, the problem with the fuel cell is a very, very sluggish response. Same thing with the turbine. The ramp up time there can be very, very long, minutes, if not many minutes. Here it can be probably in the microsecond time domain in terms of responsivity. So he's going to set that up and get that fired up for fuel, and then Johnny's purging his system. So if you want to just turn the lights off, sorry about that, Jim. We'll go right through these videos, and then we can get you back to work. Off. So this is a system running, 3rd generation. Now, one issue here is we don't have perfect. We don't have the water rinse system running now. This is reused fuel, used multiple times, and the strategy there would be that we would have the. I wonder if this laser is showing in the dark. Let me see. Yeah, so we'd have. Oh yeah, a little bit. So you can see the top here. We have PV panel. So we're throwing some of the fuel up there, it's coating it, plus we have some of the dust that gets accumulated there. So we would have a very, very high gas flow here, plus the water jets to be rinsing it down in this reservoir. So this thing would be constantly like a dishwasher, rinsing the stuff down, sucking it in and spraying it back, and the fuel pumping into the ignition area where they two rollers meet and compress the fuel and cause the ignition. So over time this gets weaker because it's getting opacified. Plus we have 2 layers of Lexon here, and we're only getting a part of the light over just this little part of the screen. Oh. So here's another one. They're building up some gas up here. Oh, sorry about that. That wasn't good. Oh. They're building up some gas up top there, and some fuel kind of accumulating up in there. It's blocking some of the light. And we're losing a lot of light down here as well. We're going to build a new design that we can kind of incorporate all that in. So that's running at, because this power supply is limited, it's 33 hertz, we should be running 100 times that. So that would be 100 times, we're feeding the fuel fast enough to go at these very, very high RPM, or high detonation rates, but we just don't have the ignition electronic switching in this old power, well, it's not old, but it's not made for this. It doesn't include insulated gate bipolar transistor kind of technology. It's just a transformer and slow switches. So ultimately we have fast switching on this. We will get a, this is argon. This is argon gas. There's no oxygen in this. We can change the spectrum. See, it's a little bit different color. There's a lot of short wavelength light in this too. Okay, so that was a inert atmosphere, and you can see here there's a line coming out. That's the exit line for the inert atmosphere. So we're going to do the demo, and then I'll come back to this slide and talk some more about what kind of power you can make out of this. You want to turn the lights on? We're going to do Johnny with the demo of the blast in argon. Wait until I get my earplugs. Hold on a second, I'm getting my earplugs. The earplugs.
Yeah, this is probably going to be pretty quiet because we have it in an enclosure. It's sealed. We've been
Yeah, it's
flushing,
quieter because you sealed it up.
flushing it with 24 liters of argon a minute for the last 5 minutes or so. Sometimes the blast can force the door open a little bit. It might get a little bit noisy, but typically it's pretty quiet. Okay, 3, 2, 1. That's what happens when you have no electricity that goes through it.
Hopefully it works and it's not snatch.
Three, 2, 1.
We get about the same. We have Dr. Glumac took spectron. We get about the same. Sometimes we get more light from the argon. It's very something in anyhow. The argon can have a lot of emission and creates black body about the same temperature as we were getting in the oxygen. So we're going to run it in an inert atmosphere in a commercial application, and the types of metals we're running are things like copper and silver that have no reactivity to water. It's extremely stable to water. In fact, for example, copper oxide is used in nuclear power plants. It reacts with hydrogen gas, makes water, and back to copper metal again. And apparently it wasn't working in Fukushima because the zirconium fuel rods got really hot in the pond, and then the water reacted with zirconium, corroded it, made hydrogen gas, and there's no copper oxide. There's a scavenger, or is used up. And a big hydrogen accumulation occurred and it exploded, as you all know. But anyhow, that's the point of it is that copper will react with hydrogen extremely exothermically at a glow red and go back to copper, metal, and water. So copper is extremely stable in water reaction. Silver doesn't react with water, and some of the other materials like nickel is also inert to water reaction. We're using titanium, and titanium will react with water, but the reaction is extremely slow, so it doesn't really affect our spectroscopy or our power balance measurements, but in a commercial system it would accumulate oxygen over the time, so we probably would not use that one in a commercial setup. The other ones that are non-reactive with water are the favored materials for durability, because we expect this to last a very long time. For example, the photovoltaic panels are, this is another question I got, the photovoltaic panels are warranted for 25 years at high intensity. The concentrator photovoltaic industry operates at 1,000 suns. We're operating at 1,000 suns, and they warranty those cells for 25 years. The motors should last easily 10 years. The rollers should redress themselves. The bearings should last that long. The heat exchangers should last an extraordinarily long time. All the components that go into this device, the mirrors should last essentially forever, should have an extraordinary long lifetime. And what I'll talk about is we're going to have different vendors make different parts and then assemble it, and we'll have the vendors warranty their particular part, like the pump, the sump pump, the ejection pump, the motors. This is made by Technic, and it's called ClearPath, the motors. So it's a known product. It's very cheap, and it's very versatile, and is ideal for this application. I was saying we got a number of choices for PV panel. We can go to gallium arsenide, we can go to single crystal silicon, or we can go to concentrator PV, either off the shelf or concentrator PV that we have custom made for our application. So one of the things that we can go over is the opportunity to increase the energy balance. Are you ready there? You want to? Keep going? Oh, ready? Okay, we're good. Want to turn the lights off? All right, it's good. So we could, how about we do this? We go out and we'll do the other one, and maybe could you do another run and we do the PV panel on it and come back?
Yeah.
We'll do that next. Yeah, that's all right. All right, so we're going to go out and do a run in the other room, and then we can come back and get the PV panel set up on this. But the PV panel you saw in the videos is a 27-watt LED light. And if you look at what the possibility is for the conditions we're running, you have to look at the losses and what parameters can be optimized. So the PV panel in the videos is 17% efficiency, and it can be increased to 40% operational in the field. We're collecting probably half the light because we're only going through a very small area on the top of the top window. We have 2 Lexan shields the light has to go through. So that can go from 40% transmitted to 100%. The firing frequency, as I was saying, is 33 hertz. We could easily go to 3,300 hertz with the fast electronic ignition system we're building now that'll run off the photovoltaic panel. The fuel thickness was about 0.1 millimeter coating on that on those rollers, and we're going to go to we can go to a 3 millimeter coating. And the electrode width is about 1.3 centimeters. And to go, if we have going back to the parameter table that I showed you, this parameter table, we're looking at 25 megawatt light, 10 megawatt. And we're saying that the fuel will be 3 millimeters high, and then we only need 3.1 centimeter width rollers. Well, if we went to 100, we can go to 100 centimeters if we have a meter by meter optical distribution photovoltaic conversion system. And the roller RPMs. This will go, we have this running in some of the videos at 2,000 RPMs. It can easily go to 4,000 RPMs or double. If you multiply these factors together, it's a factor of 5.4 million which takes the 27 LED light up to 150 megawatts of LED light. So I just tell you, we can get extraordinary amount of power from this type of design. And then looking at the cost considerations and timing. So in conversations and meetings with our engineering firms, we feel it's reasonable to look for a 16 to 18 week delivery of a 100 kilowatt electric field testable unit. The management estimates for that in terms of cost are between $30,000 and $50,000 for one-of-a-kind custom-built system, which translates in the lower end at about $300 a kilowatt. The limiting cost, once you get into producing systems in a commercial manufactured product volume and format, will bring this price down dramatically. One of the limiting costs is the photovoltaic, because no matter how big you build it, whether it's 100 kW or 10 megawatt, it's basically sunk cost in all the controls, control electronics, switches, and the ignition system. So the ignition system we're making will be expandable as a modular unit, for example, putting in a larger width roller, say going from 1.5 centimeter to 100 centimeter, can get us up by that factor of about 100 more times in power. You can change the rotational frequency, the fuel thickness, and several of the other parameters can easily get you over that power range with a modular base ignition fuel regeneration system. And then you match it with the appropriate scale optical distribution and photovoltaic conversion system. So most of the cost is, and certainly in the expansion of the capacity, in the photovoltaic cost. The mirrors are just pieces of glass, and then there's some aluminum framing or some sort of framing, and then there's the PV cost, which is the biggest cost. If you go triple junction concentrator photovoltaic, we have vendors quoting us $100 a kilowatt operated at 1,000 suns. And if you go gallium arsenide at 1,000 suns, it's about $4 a kilowatt. And if you go crystalline silicon at 250 suns, it's about it's at 250 suns, it's $4 a kilowatt. So give you an idea, where does this number come from? Crystalline silicon solar cells are about $1 a watt. So it's about $1,000 for a kilowatt. But we're running 250 suns. So you divide the 1,000 by 250, you get $4 a kilowatt. So the advantage is you're running extremely high concentrations, brings the cost down a factor of 250 times that of conventional solar energy. That is a big, big deal. That's a lot. So if you want to look at the cost, it's basically the cost for the PV. So the payoff time for 100 kilowatts is 100 kilowatts divided by 15 cents per kilowatt hour divided by 24 hours per day is 28 days. So you can pay it off in 28 days. If it's $4 a kilowatt, the payoff is achieved in 1.1 days. So our model is to basically give the equipment to distribution companies. So we'll have OEMs make the equipment, and then we'll lease it with equipment provided with some rated bus bar electric DC power. And as I was saying, the parts will be warranted by the OEMs for their particular components. And you got that going? We can leave it set, right? We're going to go? All right, we're going to go with Jim's thing and then come back to this. so the, getting back to model. Thanks a lot. A little electricity production. Kind of on the spur of the moment there. Yeah, Jim was putting this together. He didn't have it running until Friday. So, I mean, everything's happening really, really fast. He's got the lines in for the rinse downs. We're going to have that. And we're testing all the fuels. I mean, it's a little variable depending on the fuel. Sometimes it's incredibly explosive. Then, you know, it just depends on some variables we're working out. So by the time we get you back for the next one, it should be incredibly more awesome than even now. And hopefully we'll have it going at much higher frequency and it'll be that multiple even more brilliant. So, so getting back to the model. So we're going to have equipment manufacturers make this equipment for us. We'll own it. Then in that regard, we'll have no first sale doctrine. That means if you sell it, then people can modify and use it for anything unless it's in their contract. And it's easier just to lease the equipment from us owning it. And then it avoids issues, technical terms like patent exhaustion and those types of things. Plus we have standing and litigation, which is really required now in terms of, because of those actions and whatnot. So there's definitely intellectual property advantages to owning the equipment. And we see a very, very beneficial model, and we're having licensees think it's also agreeing with it. It's an ideal model from everybody's perspective, that we have original equipment manufacturers make the equipment, then we'll lease it to distribution companies, and then those distribution companies will sell power under power purchase agreements. So with the warranties coming through from the manufacturers and assemblers. It will also have product liability coverage coming from those entities. Then the distribution company will get DC power. We're encouraging DC power because the inverter, the electronics to convert DC to AC is probably a very big factor, larger than the capital cost of the equipment we're providing. Again, our equipment payoff period is extremely short. And the reason why DC is being favored by us is because, of course, the high cost of conversion equipment, plus everything uses DC. As Jim was showing here, these are electronically commutating DC motors. The motors in the Prius, the hybrid cars, in the Volt, in the Leaf, Nissan Leaf, they're all DC motors. The motors in your washer, dryer, the compressor, your air conditioner, all that's DC, lighting's DC, all your electronics is DC. It's AC transmitted because of historic considerations, but there's a incredible amount of losses going AC relative to high voltage DC, plus you have to convert back to DC, you lose a lot of the power there, maybe 20%. So we're just going to encourage DC, so we'll have DC in cars, we'll have DC in ships. They're running ships now with turbines, electric motors. Of course, aircraft carriers are electric. And then trains are electric. And submarines are electric. Cars are electric. Electric for houses is electric. And then ultimately, airplanes are now going electric. If you go on the web, you can look at Airbus. It's got something called an E-plane. It's an electric motor-driven turboprop. It's a really beautiful aircraft, and it's running with electric motors. So there's incredible advantage going all electric. You lose the fuel weight, and the device can be extraordinarily small. So and it can go forever without any fuel because it can suck the 3 to 5% water vapor out of the atmosphere. So in terms of no pollution, that's very important. No pollution. Nothing. No pollution at all. It makes a form of matter that's so extraordinarily stable, you can't even see it. So it's so non-interactive. You can even see nitrogen. I mean, nitrogen's really inert. You breathe it. 80% of the air you breathe is nitrogen. Nobody worries about this. This stuff makes nitrogen look like the most reactive. It looks like a bomb. I mean, this stuff is extremely stable. So it's lighter than air. It goes out of the atmosphere. So from all forms of pollution, no CO2 in the atmosphere. So all that greenhouse concerns goes away. And of course, there's all kinds of other advantages in terms of the availability for everybody to have an inexhaustible cheap power supply. And then where you say, where does the market go? Well, one way it could go is the following. We're planning on making a 250 kW to 10 megawatt scalable modular block. So by a block we mean something where you can put a different optical distribution system, optical distribution photovoltaic conversion system, and convert more light into electricity. So you provide more light by running it faster or putting a bigger roller in, etc. 250 kW is 333 horsepower. That's very good for an automobile. 10 megawatt, as I was saying, will power the largest bullet trains, huge cargo ships, and put multiple on airplanes. You can fly airplanes with it. So to cover that range will cover everything. So you say, well, how about a house? That's only, on average, a house is 1,000 watts. Well, if you have everything around you powered up by this, you're probably not going to hook up to the grid. Like right now, we would take all your cars and we plug it in here, and just one of them will be enough power for our building, maybe 2, 3 when we have a huge demand for power. So if you have electrical vehicles running this all over the world, you'll probably not need a grid. Why will you not need a grid? Because there is 100 times more electrical capacity in cars than there is a grid. Minimum, just counting cars. The grid is a very, very small fraction of electrical of power generation, which could be electrical. So if you say the electrical generation of the world, the grid would probably be about 0.2%, maybe smaller, maybe 0.1%. So it's a very minuscule fraction. Can't see having trillions of dollars in infrastructure to maintain something like that. It's just the technology never existed before that you'd have something so portable. You'd have ubiquitous generators with 25-year warranty with no fuel cost. You can plug in anywhere you're at. So our model is we don't care what you use it for. We don't care what you're doing with it, just as long as you don't break it with your inverter or whatever your power conditioner. You have to warranty it for that. And we say, here's a block. We'll give it to you. You plug it into whatever application you want, and we split the revenue. That's basically it, no matter what it is. So it's all a revenue stream that we share with distribution companies based on power sold. That is like kilowatt hours. So let's say you get a car. Well, you can own your seat, and you can own your steering wheel, and the wheels, and the chassis, and all that. But the electrical power source, BlackLight would own. You can own the electric motors, the transmission, whatever, control electronics. But when you switch ownership of the car, you have to call up the distribution company and switch over the contract for the electrical power. Same, you don't get infinite gasoline from Exxon, and you don't get infinite satellite radio, or if you buy a house, you don't get infinite gas, electric, sewage, water, etc. So you got to call up and say, I bought this, whatever it is, Chevy or BMW or Mercedes or whatever, and I'm switching over the contract, and then it's just so much per mile or so much per hour. Same with ships, so much per day, so much per nautical mile. For power, it's so much per kilowatt hour if you're using some electrical load, a traditional load. So that's basically it. It's very, very simple, and we've already signed a memorandum of understanding for Canadian territories, and it's a really pretty huge deal, and we're talking to a number of other companies on the distribution side and the OEM side. I think there's incredible opportunity here. I was talking to one PV company, and they were saying, well, how big is the market, how many megawatt? And I said, we're talking terawatts. I mean, this is not a trivial market. So there's an enormous, enormous opportunity here for new business. And we're making it very, very simple and very, very flexible. So this kind of shows a little diagram of how that would flow. And we are filing incredibly strong patents that I'll show, but this just kind of shows a breakdown. If you have a megawatt unit, how many hours there are in a year, and the average energy, this is pretty cheap. It's like 10 cents a kilowatt hour. You use it 70, if we break down the cash flow here becomes astronomical. Let me give you one example. You take a 250 kilowatt car, and you say 250 kilowatts times 24 hours per day times 365 days per year times 15 cents a kilowatt hour, that's $328,500. The money just becomes incredibly phenomenal what the electricity is worth. So there's a huge incentive to get out there and get units in the field. We've been filing a lot of IP. You know, all this stuff we've been filing very, very extensively on. So we have a very, very strong patent portfolio. And you know, we're really open to business to get both OEMs and distribution companies. So I think we're going to have some validators later. We have Dr. Rahman Kachari, which has been here before. We have Dr. Glumac, which is he's going to come in by Skype, and we have Joe Rennick, who's with one of our licensees, Applied Research Associates, have one of their headquarters in Albuquerque, New Mexico, but they have about 50 facilities around the country, and an extraordinarily talented pool of about 1,500 scientists and engineers, and they're working on defense applications. So I think for now what we'll do is we'll go off into the other room, see the photovoltaic conversion demo where we do the 1 hertz so you can see the energy balance. We'll come back here, take Q&A, and then queue up some of the visiting validators either directly here. We have 2 here, and then one we're going to have Skyped in.